pleasure to be here this morning and to tell you about something that we've been doing here in Canada that is really quite unique and which we regard as a tremendous scientific opportunity. And I'm going to talk about pretty complicated technical things, but I want you to watch and listen such that this is a story. It's a story that is a human story. It's something that you might say, what does a kid from Cape Breton with no musical talent like to do, which is my situation, but more important, today that's a pretty good context. More important is to recognize that this is the Sudbury Neutrino Observatory scientific collaboration. And for more than 10 years there have been a group of individuals from all over the world who have been motivated by really what is a unique Canadian scientific opportunity, but really a unique international scientific opportunity that has come about because of some natural advantages we have here in Canada, in which we can study with detail that has been previously impossible neutrinos that come from the sun and that we detect in an underground laboratory in Sudbury. Our objective in doing this is to attempt to understand our universe as completely as we can. And we're involved, as Barth, who spoke to you earlier this week, is in attempting to understand our universe all the way from the most microscopic regions to the largest scales, to the evolution of the universe in the largest scales and the longest times. And what's fascinating about this process is that if you are going to understand what's happening on the largest scales and the longest times and what happened back in that original Big Bang, you really have to understand in detail what's happening with the particles themselves at the most microscopic level, because in that original Big Bang there were energies that are far beyond anything we can create on Earth. It's one of the reasons why we're using the sun as the origin of our neutrinos, is because you simply couldn't produce the numbers of neutrinos on Earth that you can get from the sun. And so the point here is to try to get a consistent picture. You want the particles to feed in with the calculations that are done on how the universe has evolved. And so to do this, this scientific collaboration, has built an observatory 2 kilometers underground to study the sun. 2 kilometers underground to study the sun? Yes. Using neutrinos, not light in this case, but neutrinos. And we have gone to the Inco's Creighton mine near Sudbury, one of the most productive of Inco's mines. We've gone 2 kilometers down to a site on one of the drifts of the mine. It's actually referred to as the snowdrift now. In fact, we've been having a lot of fun with the snow name over the process of this project, and when you work on something for more than 10 years, you've got to find something to keep you alive. So this is the snowdrift. It's 2 kilometers down, and everything that you will see that we have built had to be brought down in that single shaft, along with the day-to-day operation of the mine by Inco, which takes over 5,000 tons a day out of that mine. What we've built is something that is quite unusual and quite unique. It's the size of a 10-story building, roughly. It has at its heart heavy water, a Canadian resource, 1,000 tons of it in a transparent plexiglass or acrylic sphere, surrounded by 10,000 ultra-sensitive light detectors or light sensors. The neutrinos come in from the sun and they produce tiny bursts of light in this detector, and we have built something that is very sensitive, can observe these neutrinos. And so some obvious questions that come out of all of this are, what are neutrinos to begin with? What's heavy water? Why did you go underground? Why is this a unique Canadian scientific opportunity? And what in the heck are you planning to learn from all of this anyway? So let's go through a few of those one at a time. What are neutrinos? Well, neutrinos are among the smallest, most basic particles in nature. They can travel through virtually anything without stopping. It's only if they hit the nucleus of an atom or one of the electrons head on that they're stopped. And so they can go through 10 million billion kilometers of lead, and there's only a 50% chance that they'll hit something in there. They're produced very extensively in the nuclear reactions that power our sun and the stars, and they were produced very extensively in the original Big Bang. They're little known because they're basically outside of normal human experience. In your lifetime, perhaps one of them will hit an atom in your body and stop, and you won't even know that it's happened. There will be a single atom changed. I usually say when I'm giving one of these talks that if it happens to be in a person's eye and that eye happens to be closed, which they sometimes are when I'm giving these talks, then they might see a little burst of light, but otherwise you wouldn't be conscious of it happening. Why go underground? Well, neutrinos, as I said, can pass through virtually anything, and so they're not affected by the rock above our detector. On the other hand, the cosmic rays, which are really the origin of the northern lights, would make our detector glow like the northern lights, except for that shielding due to the 2 kilometers of rock. Neutrinos are very difficult to detect. We only see about 1 an hour. And so having no other sources of light is extremely important. And so we've taken great care to make this the lowest radioactivity point we think that has been created. The water in the middle is about 1 billion times purer than the typical water that you would find in your tap, and that depends, of course, on where your tap is these days. What is heavy water? Well, it's a naturally occurring type of water. There is what's called an isotope of hydrogen, which has an extra neutron in the nucleus. The proton is what makes the chemistry, and therefore it behaves essentially the same as water. And in fact, these heavy water molecules we have are picked out of the Great Lakes by a chemical process. It's called heavy hydrogen in the case of the deuterium, and the water is about 10% heavier, and it's referred to as heavy water. It's used as a so-called moderator in the Canadian-style nuclear reactor. In our case, those neutrons are great targets for these neutrinos from the sun. The neutrinos do not interact with the protons, but they do with the neutrons. And so having this enormous vat of 1,000 tons of neutrons, if you like, produces a beautiful target for neutrinos and gives us a unique opportunity. My daughter told me you could go on the web and get waving flags, so I decided I would do that. Why is this a unique Canadian scientific opportunity? Because Canada has these large reserves of heavy water, which it uses in its style of nuclear reactors. This heavy water is on loan to us by Atomic Energy of Canada with help from the Ontario Power Generation. Its value is $300 million. We're taking very good care of it. And we also have an ideal underground location being provided by INCO, essentially at cost, of the operations. And that combination of a government, industry, and in our case, university collaboration has been wonderful. And we have been involved in this for over 10 years. It has been a tremendous process of sticking to our scientific objectives. And we've been in operation now for about 6 months, and we're very excited because we are observing neutrinos and having a great time. And when I say we, it's this team of over 80 scientists, many, many students who have been trained to date and who are being trained in the process of what we're doing right now. And this really is an educational exercise. And it's been wonderful from that point of view. We can have Canadian students work in Canada on frontier research and learn things that are extremely fundamental, like what is the universe like at its most microscopic level? These are the general terms for what we're studying. How does the sun burn? How does the universe evolve? And how do we do that? Well, at the most microscopic level, neutrinos, electrons, and quarks are the most basic building blocks as we know them today. We don't know how to subdivide those any further. But neutrinos, because it's so difficult to detect them, are the least known of these. And there are some properties of neutrinos which are basically unknown. We don't know whether among the 3 types, which we do know to exist, there are transformations that can take place between them. We don't know how large the mass of neutrinos is, and these are very important questions in terms of attempting to understand the microscopic theories of physics, which work extremely well right now, but which put in a postulate of zero mass for neutrinos. And the next stage of unification, as it's called, at the most microscopic level, requires that you put in finite masses for neutrinos, and what the values of those masses are is very important in terms of trying to understand the next phase of our universe at the most microscopic level. We can also study how the sun burns. These neutrinos that we observe predominantly are the ones that come from the sun, produced by these nuclear reactions. So far, all measurements of neutrinos, and there have been about 4 definitive measurements so far, observed too few of them by factors of at least 2 or 3. Now that's either because we do not understand the energy generation properties in the core of the sun, and in other ways it works perfectly. Or it's because the neutrinos themselves are changing their type, for example, and reaching us. The other experiments would not be sensitive to that. Snow will be, and that's a central question that we can answer. And if they do change their type, it means they have a finite mass, and we can measure the difference in mass between the 2 neutrino types that are involved in this change. And that is very important in terms of this question of how the universe evolves. What Barth told you about was very, very basic experiments dealing with the question of how the universe evolves, of whether it goes on forever, whether there's a big crunch in the future. Turns out there are more neutrinos than any other particle, other than the light that he is studying, left over from the original Big Bang. If the neutrinos have even a tiny mass, then they may be a significant part of this dark matter that's attracting everything else, and they can influence its future evolution. And our information about neutrino mass can help us understand, therefore, the universe on its largest scales and its longest times. However, as I said, this is a human endeavor. We have worked for many years to build this very sophisticated, very delicate, really, in spite of its size, experimental instrument. It is deep underground in a dirty mine. In the drift outside the mine, there is the standard amount of mine dust. We have built this in such a way that there's no more than the amount of dust that you could pile on a loonie over all the surfaces of this by having ultra-clean environment at all times. Everyone who came in, once we finished the excavation, put on clean clothing, took a shower before they did, and we were able to maintain that cleanliness, and as a result we have now achieved the radioactivity levels that we sought to achieve in the first place, which is that in this 1,000 tons of heavy water, there was no more than 1 radioactive decay per day per ton of water. Very, very low radioactivity. It's a sophisticated instrument, and what I'm going to show you is the sequence of construction of this instrument, and then I'll tell you a bit about how we detect the neutrinos. And so we started out with the very competent miners of INCO excavating this cavity 2 kilometers underground, 10 stories in height. And then we took that cavity and coated it with a Canadian invention, which is Uralon plastic covering the walls. It makes it sort of like a big bathtub enclosure. And so we started to create the first of the 2 snowballs that you saw in there. There's that terminology coming in. In fact, this geodesic structure that's used to hold the light sensors is suspended by Vectran ropes, low radioactivity ropes, sort of like a snowmobile, actually, if you think of it carefully. The 10,000 light sensors are extremely sensitive. They can detect a single photon of light with a 25% probability of observing that single photon. They are installed in carefully covered panels. We then set about building this sphere inside the sphere of phototubes, and that sphere of acrylic is 12 meters in diameter and about 5 centimeters thick. It was built from 120 pieces bonded together in location. Took several years to do it, and it has been done perfectly because of the value of the heavy water containing it. These are the light sensors surrounding it. This construction process, again, with a Canadian company, Menenco Canadam, supervising, was a wonderful exercise. You can now see the light sensors looking in at the central volume just before it was closed, and finally the full detector. And now maybe you can understand what that picture was I had up that looked like such a wonderful design in the first transparency, the design element of this. This is an actual picture of the detector with the widest angle lens I've ever seen poked in the bottom of that sphere and looking up. And this is the actual acrylic sphere, and these are the 10,000 light sensors looking in at it. It has been closed and filled with water for about a year now. And for the first 6 months, we made improvements, and we froze our detector parameters as of last November. And we have been taking wonderful and very exciting data since that period of time. Tremendous lengths were taken to produce this pure water. We are continually recirculating it. We had to develop technology to achieve this. We also had to develop technology to do other things, like to calibrate our detector. And this is a device actually built by a team involving very largely a group of students at Queen's University, which can move a calibration device around inside this sphere and place it within about 2 or 3 centimeters anywhere you want. I want to emphasize the student aspect of this, because with students you get wonderful whimsy. And when they were testing this device on the side of the physics building at Queen's, they set it up one evening, put a blue LED on it, and programmed it to spell out SNO on the side of the building as their proof that they were able to do this to within 2 centimeters anywhere you want on command, and control it, in fact, from anywhere you want. We can observe the events coming from our detector anywhere in the world and via the internet. And you probably know, but maybe you don't, that in fact the World Wide Web was designed by a physicist at CERN, a particle physicist, exactly to do this, in order to be able to communicate results of fundamental experiments. So here's a simulation of the neutrinos streaming out of the sun, bombarding our detector, and encountering these oxygen and hydrogen and deuterium molecules. This is the hydrogen, and you see there's an extra neutron in there in the deuterium. That enables us to observe 2 reactions. This one, in which essentially the deuterium is broken apart and the neutron then produces light, is sensitive to all neutrino types. This one, in which you have a neutron transformed into a proton producing a burst of light also, is sensitive only to the type of neutrinos produced in the core of the sun. We observe the light by the pattern that is produced on our light sensors. And in fact, this is actual data from the experiment. We observe a neutrino about once an hour. We time the arrival time of the light at the detectors, and we can go back and determine, using that travel time, where within the experiment the light was produced. This is a total spread of 10 billionths of a second of the light arrival time. And that's our way of telling where the neutrinos occurred and what direction they're heading in. So we observe neutrinos like this when you see about 100 or so of these photo sensors hit, in this case of a neutrino. This is what happens from a cosmic ray. 6,601 of them registered light, boom. Fortunately, by being so deep, this only happens about a few times an hour, and so it's no problem for us. If we did it on the surface of the Earth, it would be impossible. And we are the deepest of the experiments that are presently operating. Other experiments have hundreds of times more of those cosmic rays than we do. We began our observation program about 6 months ago, and the detector is running extremely well. Our radioactivity levels are what we had hoped, and our ability to observe neutrinos is essentially what we had intended. On the other hand, at 1 per hour, in order to get the statistical accuracy and in order to spend enough time doing the systematic checks to make sure that you have everything very accurate, It will be a multi-year program in order for us to address the many fundamental questions that we can address. Philosophy. I've been struck in this conference by the different ways in which people are talking about their relationship to their universe. And we have a very unusual and very technically detailed way of approaching our universe. On the other hand, the motivation is the same for all of us, and that is to attempt to understand. What motivates scientists, and what is absolutely wonderful about all of this, is that the more detail that you obtain about your universe on the most microscopic level, or even on the largest level, the more beautiful and the more orderly it appears. In fact, scientists have the feeling that if what you have observed is not something that you can put in order, then maybe it's not the way nature is working. And what's wonderful about what we've been able to find so far is that it has become more and more orderly as time goes on. And I'm also very conscious of things similar to what Douglas Cardinal said last evening, and that is we are building upon the information obtained by our elders in terms of our understanding of the universe. And we are just going that next step. And what has been obtained in the way of information and what has been put together in the way of a synthesis of how we understand our universe to date has truly been remarkable. And we're privileged to be able to participate in this. The activity that we have been doing here in Canada has attracted the attention of scientists all over the world, including someone who has, in fact, provided more order than most in terms of our understanding of the universe. We were privileged to have Stephen Hawking visit our laboratory, in fact, the underground part of our laboratory, several years ago. We are, in fact, hosts to the world again next week. We have a major international conference, the conference in the field of neutrinos, taking place in Sudbury. We will be talking about our first 6 months of operation, and so it's very timely from that point of view, and we're very conscious of being hosts to the world in this case. The capabilities of our detector are also such that we can interact with the world in other ways. We are, as a community of scientists, very conscious of breaking down international boundaries and concentrating on things of common interest. And our detector as a supernova detector of a collapsing star does take place every now and again in our galaxy. They take place throughout the universe much more extensively. If that occurs, then we see 1,000 events in a few seconds rather than one per hour. We are connected with other detectors around the world because we will see through neutrinos the existence of such a collapse hours before the light will develop. And so we are in a network of detectors around the world with the intention of alerting astronomers, and in fact we're part of a target of opportunity, as it's called, for the Hubble, to turn it in the direction of such a supernova if it occurs. So we're internationally collaborating from Canada. We are attempting also to make sure that we speak to the general public as extensively as we can about what we're doing. If you're in Sudbury, I encourage you to go to Science North. It's a wonderful science center, and we've worked with them to produce a way of describing what we're doing that we hope is understandable in layman's terms, and that can grab young people, as I was grabbed many years ago by some very good teachers, to get involved in this type of activity. And so we do it with great interest because of what we can observe. We do it with great effort in order to achieve what we can, but we also do it with a certain sense of whimsy. For example, do you know what a snow fence is? That's the person we sell the heavy water to at the end of the experiment. Thank you.